This video is about harmonic oscillator, which is just a special case of oscillatory motion. An oscillating motion is any motion that repeats itself back and forth around an equilibrium position. Some classical examples are swinging clock pendulum moves back and forth due to gravity, waves on a water surface, or more exotic cases such as light that can be understood as an oscillation of electromagnetic fields. Even though harmonic oscillator is a special case, it's an extremely useful model because many real-world systems approximate harmonic motion very closely, such as atoms vibrating in a solid. They often behave like tiny harmonic oscillators. Of course, in reality, many systems don't perfectly follow harmonic motion. But even in these more complicated scenarios, harmonic oscillators serve as a foundation. They give us a simple starting point to understand oscillations before diving into the more complex behaviors. This video covers the simplest example, which is a mechanical oscillator, a mass on a spring. And we will focus on the idealized undamped harmonic motion. Okay, let's set up the problem. We have a mass on a spring. The spring is attached to the left on the immovable wall. And on the right here, there is an object that can slide along the surface to the right or left. The system is characterized by two key parameters. The constant K, which is also called the stiffness of a spring or a force constant, the mass m of the object attached to a spring. Because there is no damping in the system, we will consider that the surface is frictionless and there is no air resistance. What we will study is the motion of the object as a function of time, and therefore we need to set up the coordinate system. There are two reasonable choices here. We choose a Cartesian coordinate system and put the origin at the beginning of the immovable ball, like in this picture. The parameter L is the length of the spring when relaxed. So in this coordinate system, equilibrium position is at x equals L. Another choice is to place the coordinate system at the equilibrium position of the spring. The equilibrium is then by definition at position x equals 0. And the coordinate x here measures displacement of an object from equilibrium. Of course, the choice of the coordinate system is ambiguous. Physics does not depend on the choice of the coordinate system. It is just that the description of the physics can be much easier in one coordinate system than another. It is then up to us to choose the coordinate system such that the calculations will be easiest. For example, we can even choose the coordinate system such as this. It will not change the physics, but the equation of motion and the interpretation of this equation will be much more complicated and ugly, so this is a bad idea. In this video, we will choose the second option, where the origin of the coordinate system is at the equilibrium position. Also, because the motion is only in the x direction, we can just forget about the y direction entirely from now on. Okay, moving on. Imagine that we stretch the spring by some distance. As soon as we do that, a force starts acting on the object. This force is called a restoring force and follows Hooke's law, which can be written as follows. You may now ask, where does this force come from? Well, it was originally guessed based on physical intuition and empirical evidence. But let's take a look at the structure of this force to see why it makes perfect sense. Constant K here is the spring constant we introduced earlier. It is always positive real number. The larger the value of K, the stronger the force. We can also determine the units as follows. On the left-hand side of the equation, we have a force, which is measured in newtons. On the right-hand side, we must also have a force. So the units of the product of these two terms must be in newtons in SI system of units. Displacement x is measured in meters in SI units, therefore K must be measured in newtons per meters. So those are units for parameter K. The displacement x is measured from the equilibrium position, so the larger the displacement, the stronger the restoring force. And this makes sense. Imagine a rubber band. The more you stretch it, the harder it is to pull. Of course, if a sufficiently large force is applied, the rubber band will eventually break. It means this law is only an approximation. It doesn't hold in all cases. But it works very well for small displacements. So while it started as an educated guess, it was eventually validated by empirical evidence and now is well established in physics. The negative sign here ensures that the restoring force always has the correct direction. Consider this. If x is 0, displacement is 0, that means the spring is relaxed and there are no forces acting on the system. If x is positive, meaning the spring is stretched, the restoring force has a negative sign and is directed toward the equilibrium position in the negative x direction. If x is negative, meaning the spring is compressed, the force is positive. This happens because we have negative value multiplied by another negative value, resulting in a positive force directed towards the equilibrium position, in this case in the positive x direction. This is why it is called a restoring force. Now that we know the force acting on the system, we can immediately apply Newton's second law, which in this case is written as follows. Mass times acceleration, which is expressed as the second time derivative of a position, equals the net force acting on the system, in this case just the restoring force. The double dot notation is just second order time derivative of x. We can move all the terms to the left hand side of the equation and divide by mass, so that we can express the equation of motion in a simple form. Here we introduced another parameter called the natural frequency of the system, and we will come back to this a little later. Let's now focus on solving the equation. It is quite straightforward. Technically speaking, this equation is a second order differential equation, homogeneous with constant coefficients. And methods for solving such equations can be found in any textbook on ordinary differential equations. We can solve it by writing down the characteristic equation for the system, which in this case has a following form. Lambda is squared because there is second order time derivative in the original equation. Similarly, if there were a first order time derivative, we would have lambda to the power of 1, which is just lambda. And x can be thought of as a 0th order time derivative, so this is just 1. Okay, we need to solve this equation for lambda. We need to find its roots. We can easily see that it has two complex roots written in this form. When I take square root of this equation, meaning which is just plus minus complex unit omega 0. Having found the roots, we can easily express the solution as a sum of two complex exponential functions like this. One can easily verify that this expression is indeed the solution by substituting back into the original differential equation. But we can see that there is a problem with this expression. It is a complex function of a real variable, which is time. But x should represent the displacement of an object from equilibrium, and it should be a real valued function. Complex function does not make physical sense in this context. Fortunately, we can get around this quite easily. Any complex function can be decomposed into its real and imaginary parts, so we will do exactly that. We decompose the constants and use Euler's formula for the complex exponential function. Substituting all of this into the original expression, we write it as a sum of a real and imaginary parts. So here we made just the substitution into the original expression, and now we can separate the real and imaginary parts. So this is the real part of the expression, and this is the imaginary part of the expression. Mathematically speaking, what we have obtained is a solution that exists in a complex domain, but we are only interested in solutions that take the form of a real valued function. Therefore, we will demand that the imaginary part of this expression is equal to 0. This condition gives us a constraint on the constants a, b, c, and d that satisfy this requirement. The imaginary part becomes 0 when both of these terms vanish. So b plus d must be 0, and also a minus c must be 0. Equivalently, we can write this as a equals c or b equals minus d. If we substitute this back into the original expression, we will have imaginary part that is 0 as required by definition, and the real part simplifies into the sum of sine and cosine functions like this. Again, we just redefine the constants and write down the solution in a more compact form. This form of the solution is likely familiar to many of you because it is often used in the literature. More importantly, we have achieved our goal, obtaining a real valued function. Okay, now that we have found the solution, let's discuss the parameter omega 0 introduced earlier. We can again work out the units to verify that it indeed has the correct units for frequency, which is inverse seconds. But what does this frequency actually mean? Does it represent the number of back and forth motions per second? Not quite. Take a look at the argument of cosine and sine function. There is omega 0 multiplied by time. And we know that sine and cosine functions take arguments in radians or angles. Therefore, omega 0 refers to the angular frequency, not the ordinary frequency. It describes how the system oscillates in terms of angles or radians. To find the actual number of complete oscillations per second, we need the ordinary frequency. This ordinary frequency is related to the angular frequency by the following formula. The frequency f is measured in hertz or equivalently inverse seconds. Its numerical value tells us the number of complete oscillations per second. So while both frequencies describe the speed of oscillations, frequency f counts the actual oscillations per second, while omega 0 describes the motion in angular terms. Okay, let's now go back to the solution we found. We found that the solution to the differential equation governing the motion of simple undamped harmonic oscillator can be written as a sum of sine and cosine functions here. Before we closely analyze the actual time evolution of the system, I want to provide a list of different forms in which this solution can be written. If you look at various physics textbooks covering harmonic oscillators, you might notice that different authors write the solution in different forms. For example, here is a short list of different equivalent forms of the solution that can be encountered in the literature. I don't know about you, but when I was studying for my bachelor degree in physics, I used multiple sources of literature, and in each one the solution was written differently, and this confused me quite a bit. That's why I want to clarify here that all these different forms of the solution are equivalent. They are all correct solutions to the original differential equation, just written differently. So I want to show that they are indeed equivalent and explain how one can transition from one form to another. Let's start with a complex exponential form. This notation RE and the expression inside the curly brackets mean that we should take the real part of whatever is inside the brackets. Here we have R, which is just a real valued amplitude, and a complex exponential. So we can use Euler's formula again, decompose it into its real and imaginary part, like this. So this is the real part of the expression, and here we have an imaginary part of the expression. And this notation tells us that we should take the real part of the expression, which is simply r times cosine function. In physics literature, we often write the solution in terms of complex exponential without explicitly writing RE notation for the real part. This is because using a complex exponential is much easier. So even though I said that only a real part of the expression has the physical meaning, we can still use the complex exponential. And this is because complex exponential is much more easier to work with than with sine and cosine functions. Complex exponentials are simple to differentiate and integrate, making calculations more convenient. But one must also remember that only the real part of the expression has physical meaning. So you can do the calculations using the complex exponentials, but at the end you have to take the real part of the expression. Sometimes we may even encounter this form, where we rewrite the exponential as a product of two terms containing the initial phase and the other representing the time evolution. We can then hide the initial phase into the amplitude, and we define something called complex amplitude. Again, only the real part of this expression has physical meaning. Another type of solution is rather trivial. In some literature, authors use cosine function, while in others they use the sine function, sometimes even with a negative sign here. As you may know, the cosine and sine function are essentially the same, but shifted by pi over 2. So one can express the solution using sine or cosine, and the solutions will be equivalent, but they will differ in the initial phase, which will be related by this formula. Okay, the last thing I want to show is the following. Taking the cosine form of the solution and using the sum and difference formula for cosine, we can rewrite it in the following form, as a sum of sine and cosine functions. We define the new constants in this way, and as you can see, we recover the original form of the solution. That concludes the discussion of different types of solution. I hope this helps you navigate between the different forms when reading various literature sources in the future. Let's now take a closer look at how the system evolves over time. I will use this form of the solution expressed with the cosine function. We know that the upper and lower bounds of the cosine function are plus and minus 1. So the displacement x will oscillate between plus and negative r. So naturally we call r the amplitude of the oscillation. The amplitude refers to the maximum displacements of the object attached to the spring. The parameter phi represents initial phase. These are integration constants, and to determine them we must apply initial conditions. The solution written here is the general solution. It includes all possible time evolutions of the system. However, it doesn't inherently know whether the system was initially at rest or if we first perturbed it in some way, imposing an initial velocity. To specify the system's unique behavior, we must define initial conditions, which can be written as follows. We specified the initial displacement from equilibrium, denoted by x0 at some initial time, and the initial velocity denoted by v0. The initial time can be chosen arbitrarily. For simplicity, we set initial time equals 0. This choice is similar to selecting coordinate system at the beginning. The choice of the time origin does not change the physics, so we might as well choose time equals 0 because this simplifies things. Once the initial conditions are specified, we can solve the equations for r and phi, which will determine the unique time evolution of the system. Let's now consider the following scenario. Initially, we displace the object from its equilibrium position by hand or by other means, stretching the spring by a distance x0, and we then release it. Mathematically, we can express these initial conditions as follows. The initial displacement at time 0 is x0, and releasing the object means the initial velocity is 0. Now we plug our solution into these two equations and solve for r and phi. From the first initial condition, we obtain this equation. From the second, we first take the first time derivative of the solution and then set time equals 0 and obtain another equation. And now we have two equations for two unknowns, r and phi. From the second equation, we can solve for phi. But there is a little complication. Sine function is periodic with period 2 pi, meaning it has actually an infinite number of mathematical solutions. However, only one of them is physically meaningful, and we need to select the correct one. To do this, we restrict our search to the interval 0 and 2 pi. In this interval, sine of phi equals 0 has two solutions. Either phi is equal to 0 or pi. So we still have two choices. If we set initial phase to pi and we plug it back into the first equation, we get r times cosine of pi, and it must be equal to x0. But the cosine of pi is minus 1. So we got for the amplitude r equals negative x0. And the displacement or time evolution of the system can be written as a negative x0 times cosine omega 0 time plus pi. And this is how it looks like. We see that the resulting solution shows that the object starts moving from the negative x position, which would physically mean that the spring was initially compressed. But this is incorrect. We set the initial conditions such that the spring was initially stretched. So the solution should start from the positive x and then move towards 0. Therefore, this choice for initial phase is incorrect. If we choose initial phase to be equal to 0, then again, plugging this into the first equation, we got r times cosine 0, which is 1, and this gives us the value for the amplitude. And the time evolution can be written as r times cosine omega 0 t. And we can see that this gives us the correct time evolution. It starts from the positive x value and then goes towards 0 and then oscillates back and forth. So we conclude that phi must be equal to 0, and for the amplitude we got x0, and solution to the original differential equation with the initial conditions can be written like this. This result makes perfect sense because the initial velocity was 0, meaning that the system begins oscillation with the same amplitude that we initially set. Since energy is conserved, amplitude cannot increase or decrease over time. Now consider a different scenario. Initially, the spring is relaxed in its equilibrium position, but we perturb the system by pushing the object into the negative x direction, thereby imposing an initial velocity. System should therefore start to compress first and then move back and forth. Mathematically, we can write the initial conditions as follows. The spring is relaxed at time equals 0, so it is in its equilibrium position. So initial position is 0 at its equilibrium position, and we impose some initial velocity, and here we impose some initial velocity in the negative x direction. And again, this gives us two equations, and we need to solve for r and phi. Here is the first equation, and here is the second equation. So we got two equations, and from the first equation, we can solve for phi. This gives us again two choices. Either initial phase is equal to 3.5 times pi or pi over 2. If we choose initial phase to be 3.5 times pi, we get this time evolution. And we see that it starts from equilibrium at x0, this is correct, but it starts to evolve in the wrong direction. You see it begins to move in the positive x direction, meaning the spring starts to stretch first, and this is not consistent with the initial conditions. Therefore, this is the wrong choice for initial phase. If we choose initial phase to be pi over 2, we get the correct time evolution, as is seen here in this graph. So to conclude, phi must be equal to pi over 2, and we can plug this result into the second equation to solve for r, and we get this value. The amplitude r is equal to the magnitude of the initial velocity, v0, and is divided by natural frequency, omega 0. Again, this makes perfect sense because the system was initially at rest. So the maximum displacement, the amplitude, should depend on the initial velocity of the system. Okay, that's it for today. If you enjoyed this video, please like and subscribe. There will be more physics videos coming.